Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Take a moment to picture the fastest animal on two legs, the ostrich. A creature weighing up to 300 pounds, capable of sprinting at 45 miles per hour. Now, picture a human running that fast. We bob, we oscillate, our center of mass, calm, violently rises and falls with every stride as we fight gravity. But the ostrich? Its head remains eerily level, cruising forward with a stability that seems impossible for a creature generating so much speed. This incredible smoothness is not just graceful. It represents a profound engineering marvel known as the Ostrich Gait Paradox, and it's currently revolutionizing the field of soft robotics by appearing to violate the fundamental expectations of Newtonian momentum. To understand the paradox, we must first look at how classical physics expects a rigid body to move. When a human runs, we essentially follow the inverted pendulum model. As one foot leaves the ground, the body is momentarily airborne, and gravity pulls our center of mass down. To prevent falling, the landing leg must exert a massive vertical ground reaction force, GRF, to decelerate the downward momentum and re-accelerate the calm upward. This constant cycle of kinetic and potential energy exchange requires intense muscular effort, resulting in that visible, exhausting up and down oscillation. The vertical component of momentum is constantly being destroyed and recreated, burning massive amounts of energy. The ostrich, however, found a loophole. Its legs are not rigid levers, they are highly compliant, intricate spring systems, a biological masterpiece of soft material science. The magic lies in the ultra-long, highly elastic tendons, particularly those running along the back of the leg. When the ostrich lands, the GRF is not immediately transmitted up to the main body mass. Instead, the compliant lower leg acts like a highly tuned shock absorber, efficiently storing the collision energy in the stretched tendons. This storage and release mechanism allows the limb to redirect the impulse horizontally, pushing the bird forward, while simultaneously dampening the vertical forces. The force profile on the ground is long and gentle, rather than short and sharp. In Newtonian terms, the ostrich minimizes the vertical impulse applied to its overall center of mass. The large momentum changes are handled within the compliant limb structure itself, effectively decoupling the massive internal forces required for locomotion from the external trajectory of the main body. This is the biological trick soft robotics seeks to replicate. Engineers building traditional, rigid robots quickly hit the speed wall. Higher speeds require stiffer components and massive motors to handle the violent impacts, increasing weight and decreasing efficiency. The solution, inspired by the ostrich, was to switch to compliant robotics, building robots primarily from flexible, elastic materials like specialized silicones, elastomers, and fiber-reinforced hydrogels. These soft robots don't need complex control systems to calculate the perfect angle for absorbing impact. The material itself performs the calculation. When a soft robotic leg strikes the ground, the material deforms and springs back, storing the energy instantaneously. Much like the ostrich, the compliant robot manages the impulse internally, allowing its main body to maintain a steady, horizontal velocity with minimal vertical fluctuation. Research has shown that soft robots designed with compliant spines and legs can achieve dynamic decoupling, allowing them to traverse uneven terrain up to 4 times more efficiently than their rigid counterparts. It's a system where local changes in momentum, the leg flexing, do not translate into global changes in momentum, the body bobbing. In essence, the compliance allows the robot to run at speeds where a rigid machine would be completely unstable or simply burn itself out fighting gravity. This isn't a true violation of momentum conservation, of course. Energy and momentum are always conserved. But the Ostrich Gait Paradox shows us that compliance offers a superior method of managing those forces, channeling them away from the calm and reducing the wasted energy expenditure that classic mechanics dictates for rigid movement. Soft robotics is proving that when it comes to movement, stiffness is weakness, and compliance is the key to faster, smoother, and vastly more efficient locomotion. From prosthetics that naturally absorb shock to search and rescue robots capable of navigating chaotic environments without losing balance, the lesson learned from a massive bird sprinting across the savannah is redefining engineering. By mimicking nature's soft machines, we are learning how to build technology that runs fast by intelligently yielding to the world around it. For more incredible facts like this, don't forget to subscribe and turn on notifications.